Okay, so let's talk about what's called the squeeze theorem. So this is a tool that's going to help us compute some limits that we had no idea how to do before, because they're just things that we can't really do any algebra on or change around much. So let's jump back to a previous example we saw that we didn't like, and that's the example of the function sine of 1 over x near 0. And remember that this is a discontinuous function. It has an oscillatory discontinuity, and it looks something like this. Draw it as nicely as I can. It's just this horrible mess near 0. Something like that. It just sort of looks like static near the middle. And this is a horrible function, but consider the following sort of related function. Let's consider the function x times sine of 1 over x near 0. So what does this function look like? Well, it's still very nasty near 0, but it looks a little nicer. So what does this look like? We have x is multiplying this sinusoidal guy, and sine is always between 0 and 1. So as it turns out, this function is always going to be bounded above by the line y is equal to x on one end, and by the line y is equal to minus x on the other end, just because sine of 1 over x always moves, for x not equal to 0, between 1 and minus 1. And indeed, the graph of this function, y is equal to x sine of 1 over x, is going to look something like this. It's still going to be very nasty, but because it's squeezed in between these two lines, we can actually sort of eyeball this, or we could use a computer to sort of guess its values. And we can sort of just see from this picture here that we in fact have the following, that the limit as x goes to 0 of x sine of 1 over x is going to be equal to 0. But how do we make this a little bit more, how can we justify this a little better? Like, of course, we can see it from this picture, but we can't draw a picture for every single example we do. So what I'm going to do now is I'm going to introduce what's called the squeeze theorem, which will allow us to justify why this limit is 0, and then we'll do a couple of examples. So what the squeeze theorem says looks a little bit complicated. I'll write it down and then I'll explain it. So it says that if g of x is less than or equal to f at x is less than or equal to h of x near c, and the limit as x goes to c of g of x is L, which is also the limit as x goes to c of h of x, then the limit as x goes to c of f at x is also L. So let's just draw a very quick and dirty graph over here. So if this is c, the idea is that the function f is being squeezed, hence the name, between the graphs of g and h. So the idea is, let's say this thing here is h of x. This guy here, is y is equal to, h of x is on top. H of x, I apologize, this guy here is g of x. And then what we have is that if this guy between them is f at x, and let's say this number here is L, all we're saying is that we expect the limit of f to be the same as the limit of these two functions above and below, because it's indeed squeezed in the middle. And that's how the theorem works. So let's just go through the example and use how we can do this to show why the function we saw previously, x times sine of 1 over x, indeed works like this. So how does this work? Well, note, for x is not equal to 0, where the function's undefined, well, we know that sine of 1 over x is always less than or equal to 1, and is always greater than or equal to minus 1. That's just because every value that sine spits out is between 1 and minus 1. Sine is a periodic function, it just doesn't go out of those bounds. But what that means is we can multiply these inequalities rather, by absolute x. So now what we can see is, unfortunately we have to break this into two pieces. For x greater than 0, what we have is that we have x sine of 1 over x is going to be less than or equal to x, which is greater than or equal to minus x. We get that just by taking this equality in a chain of inequalities and multiplying it by x. For x is less than 0, when we multiply by x, we have to switch the directions of the inequalities since we're multiplying by a negative number. And we get that this thing is greater than or equal to this and is less than or equal to minus x. But we can put these two into just one line by using absolute x. So we can see here, this is absolute x because x is positive. Here, this is absolute x because x is negative. So in fact, in all cases, when x is not equal to 0, we get that x sine of x is less than or equal to absolute x. And for exactly the same reason on the other side, this whole thing is greater than or equal to minus absolute x. So how can we use the squeeze theorem here? Well, we're going to let this guy be our f at x, this guy is going to be our h at x, and this guy is going to be our g of x. And we can easily see that the limit as x goes to 0 of h of x is going to be 0. We see that the limit as x goes to 0 of g of x is going to be 0, which is very similar to things we've seen before. We can graph these two out, work with them very easily. If we want to be a little more explicit, we can use left-hand and right-handed limits. Nonetheless, it's all going to work out. This is true, and therefore, because this function is squeezed in the middle by the squeeze theorem, we're going to get, indeed, that the limit as x goes to 0 of x sine of 1 over x is 0 as well. And we really like this because we don't have another tool to work with a limit like this, because we can't do any reasonable algebra on this quantity sine of 1 over x. This is sort of our only recourse to be able to compute a limit like this. But with a little bit of pre-calc inequality stuff, we get these bounds, and then we can plug this, along with this fact, right into the squeeze theorem to get the limit we want. Okay, so let's do one more example, and the fact of the matter is, the picture I drew when the theorem I stated was for limits at c, but this whole squeeze theorem process is also going to work for limits at infinity. So let's just do another example, sort of imagining, we know everything works, just replace c with infinity, and we can do those limits. And let's do something similar with the limit as x goes to infinity of, and let's just take something here like x squared plus sine x all over, say, 2x squared minus 3. So we can, once we're familiar, sort of eyeball this limit and expect it to be 1/2. Why? Because this sine of x, it just oscillates between 1 and minus 1. So it almost just behaves like a constant, and you have a degree 2 polynomial on the top, a degree 2 polynomial on the bottom. The limit should just be the leading coefficient of this divided by the leading coefficient of this, which is 1/2. But that's not quite good enough, and we need to go we need to do a different thing in order to actually justify that. Of course, the logic is sound, but we still want to cover all of our steps. So what can we do? Well, we can use the squeeze theorem here. And how do we do that? We just have to establish bounds. Well, what we can say is we know, and this is basically the same as what we did on the previous example, we know that sine x is less than or equal to 1, and it's greater than or equal to minus 1. So, well, we can always add to inequalities. This means that x squared over sine x, x squared plus sine x rather, is less than or equal to x squared plus 1, and is greater than or equal to x squared minus 1. So now note, for large x, 2x squared minus 3 is positive. You can take a quick graph of that, and you can see so long as x is very large, this is going to be a positive number. So assuming x is sufficiently large, which we can always do in this case, we can divide this whole inequality out by 2x squared minus 3 to get that this thing we want is less than or equal to this, is greater than or equal to this. Now, I'm doing this fairly quickly, but indeed, from methods we talked about in previous videos, you can very quickly do exactly what we did there and see that the limit as x goes to infinity of this first guy, x squared minus 1 all over 2x squared minus 3, well, this limit is, like I said, going to be 1/2. We've already seen techniques to establish that. And as will this guy over here, for essentially the same reason. And since we have these two outside guys, our g and our h, if we like, having a limit and having it be the same limit, that means that by the squeeze theorem, we can indeed say that the limit as x goes to infinity of what we want also goes to 1/2. And that's how you can use the squeeze theorem in practice.